Systems Lab, we are going to obtain system response of the system in different methods in both time and frequency. So you have already known that a signal passing through a system, it's called convolution in time domain. So the properties of convolution in frequency domain is called multiplication. So you can just simply multiply the Fourier transform of input and the system. Then you will get the output. So if you want to get the system, what you will do, you just simply divide input to the output. There are three methods which we can use to find the system response. So the first method is, this is not practical one. We will simply put different type of frequency, different frequency value, sine wave, and then we will observe the output in frequency domain. So here we will use 20 different frequencies starting from 10 until 2 kilohertz. Let's say we have this system, LTI system. So we have no information about that. What is R, what is C, we don't know anything. And we will give 10 kilohertz sine wave, and we will get the output and see the Fourier transform and get the frequency. So repeat many times, 20 times. And then at the end, you got the graph in frequency domain. This is called transfer function. In time domain, it is called system response. In frequency domain, it's called transfer function. So you got the transfer function, but you have no information about the transfer function. So what is the cutoff frequency you need to find? So this is in frequency domain. Okay, this is F. So the input is 10 kilohertz, output is here. It is 20 here, somewhere like that, until 2 kilohertz you will use. So initially this is, let's say, 6 dB you have. Okay, according to what is your input, 1 volt or 2 volt. We have the formula, right? So the second frequency is still 6. That's still 6. So until somewhere around here, you will see it become 3 dB. So from 6 to 3, so you have drop or minus 3 dB. So this is the point where you will find the cutoff frequency. This is called cutoff frequency, FC. In this system, we already make it 1.6, so you should get 1.6 here. So this is our system. Okay, it's actually low pass filter. Input coming from R, output is between this, and this is the ground capacitance. Okay, first of all, we will give the sine wave with 10 Hz. Peak to peak is 2 VBB, so the amplitude is 1. The blue one is input, yellow is output. So you can see it's 10 Hz for both of them. Okay, and we have to do it 20 different frequency. We have to see the frequency in FFT domain. I measure using cursor, and I measure using frequency, type is frequency. So we get both frequency and magnitude together. So eventually we get minus 3 dB here at 10 Hz. Okay, so we will do it 20 times, but I will only just do it 10 times. So use second frequency. Okay, same amplitude. Okay, and then write it down for 10 Hz, okay, minus 2.9 we got. Okay, 50 Hz also still minus 2.97. Previously also minus 2.97. Okay, I will change now to different 100 Hz. So while I'm doing it, the frequency cursor is not moving well, so I will just use magnitude cursor. Here I just go to the top, the peak, still minus 2.9 at 100 Hz. Let me jump to 300 Hz. So at some point, the frequency will keep going up, so you will not see it anymore. At that time, you have to scale it. Here scaling, okay, it's 2.5 kilo sample. So this is sampling rate. So it should be twice the original frequency. I will make 2 cursor. The first cursor will be placed at the initial point, which is minus 2.9, and then we have to see it drop to minus 3 dB. When it is dropped to -6, it should be our cutoff frequency. So let's put the initial point -2.9. Casa 2 is -2.9. I will not move Casa 2, only Casa 1 when we move. At 300 Hz, we see it's -3.37. I'm just randomly moving 1.4 kilohertz. Okay. 1.4 -6.57. 2 kilohertz -8.57 dB. Okay, so this is our final frequency. Actually, because I know this is frequency, cutoff frequency around 1.5, 1.6, that's why I stop at 2 kilohertz. Let's say you don't know any information, so you have to keep trying. So the second part is we are gonna use input impulse, unit impulse signal as an input, which is a delta function. And according to the convolution formula, we have, if we convolute impulse with a system, what is the output? The output is the system impulse itself. Here you can see it's called pulse, and we can change the width of the pulse. Impulse means the width is very small. So for example, if I make it, do you see? The width is big. Look at this, is not impulse. This is like square wave. I will make it 0.1 millisecond. If I zoom in, still it is very small. So this is the pulse. So this is our system response. The low pass filter impulse response function is exponential function. Okay, so exponential multiplying with the step function. The P2P voltage is now reduced. Let me zoom in a little bit so you can see this is the actual shape for the impulse response. So the last part, we will use the unit step function. We will use the same circuit, but we'll use different RNC value. When you do convolution between unit step and the function, you will get this one. It's just an integration. Unit step is everything is 1, so you are left with this. And then if you want to get this, you should do differentiation of the output. So the procedure is you give the unit step function as an input signal, and then you will get the output from the system, and then you will do differentiation of the output. The input here is the output of the system. So this is the RC circuit, okay, R and C. This is, I don't have 10 microfarad, so 5. So this is the input unit step function. So we will see what is the output first, and then we will give this output to our integrator circuit here. We don't have unit step function in the function generator, so we will just use square wave. So in order to make it, it should be very long width. I use a unit step function from function generator with low frequency. I just randomly put 2 VBP. So only minus, and then it should be 1 here. So it should continue going, keep going. Okay, it shouldn't go drop. So this is the output of the system. And now we will give this to the differentiator circuit. The open circuit is differentiation circuit, so it's the differentiate the input V in, whatever the input signal, and then the gain is minus RF C in. So this is the blue one is input unit step function, okay, and we give the unit step, and the output of the unit step, which is a system, it's this one. We already know like this. Okay, we are interested in only this one period, and I give this yellow signal to the second circuit. So this is the output. So when the step function is positive, consider this is 0. So we don't have this. Okay, so only this one. So it is look like our system response from second part exponential function. Why do we have it down here in this after we differentiate? The reason is open, we are using from the inverting open, so minus. And also you can see the formula here. What should I do if you want to get the positive? So you just simply do another open, not differentiator circuit, just summing amplifier. So if we don't have another signal, it will give you the output as it is. So let's check the amplitude and frequency. Frequency is same 10, amplitude is 2 VBP, but there is gain. So the blue one is the input of the differentiator. So consider this is 0. it keep going. We have a gain, some gain in the output of differentiator. Okay, 3.4. This is 1.8. The reason is this formula, right? You can check R, F, and C in. After that, using the equation A, you need to get the HD. So here, YD is the output of RC circuit, which is the blue one. You can write it mathematically, and then you will do derivative, differentiate this function, and you will get some expression. This expression should match with this yellow curve. So that's it for this lab.